Okay, we are now going to apply Newton's second law of motion to rigid bodies, and we're just really going to look at planar motion moving forward. So Newton's second law, translation is going to be the same as it was for a particle. That would be the sum of the forces equals the mass times the acceleration. This time we use the acceleration of the center of gravity for our rigid body, but still it's the same equation. Sum of the forces equals mass times acceleration. Difference here is when we get into rotation. Okay, so what we're doing here is we've got a rigid body here. Okay, and I am looking at a single particle. We're going to look at an infinite number of these particles, but at one particle I've got internal, external forces on it. It's some distance away from some arbitrary point P. Now, all I'm concerned with is the external forces. The internal forces are all going to cancel one another because there's always going to be another particle with an equal and opposite force acting on it. So basically, I just take R cross Newton's second law. So I have R cross F equals R cross MA. So that's where I'm starting. I'm looking just at this single particle, and we're going to move on to all the particles as we move through. So R cross F is simply the moment, okay, about point P of this particle. Okay, and then for this one, I pull out the m, put it with the r, which I can do because m's a scalar, and I'm left with ai, which is the acceleration of the particle I, and I write that in relative to the acceleration of point P, which is what we just went through in the last chapter, which is AP alpha cross r, omega squared r, right? And I do this cross product, so I have r cross A, r cross alpha cross r, and then omega squared r cross r. R cross r is going to go away. That's going to go to 0 because any cross product times itself. So what I'm left with here is just the r cross A and the r cross alpha cross r. Okay, and I'm calling r vector just xi and yj. So that's what I plug in here. Okay, so again, I pull my m out, my scalar out. Okay, I'm looking here. I'm just going to take, this is r cross A, that's what I have here, xi plus yj plus apxi plus apyj. That's the acceleration of point P, plus r cross alpha cross r, that's what I have here. There's r alpha r. So I perform these cross products. Okay, everything is now in the k direction because it's a planar motion. All moments are going to be in the k direction. So I drop my vectors here, go through my cross product. And what I'm left with is, again, the mass times y times apx, x times apy, and then I have x squared times alpha and y squared times alpha when I perform the cross product. Okay, now alpha times x squared plus y squared. X squared plus y squared, Pythagorean theorem tells me that's r squared. So I replace the last term with just alpha r squared because x squared plus y squared is r squared. Okay, so that is the moments about point P of that particle I, or on that particle I. Now what I do is I sum up all of my particles. So I sum up all of the external moments about P that are acting on all of the particles. Okay, and basically I'm summing everything up. So instead of mi, I switch that to dm. So that's where these dm's come from. So rather than the mass of the particle, it's an infinitesimal mass dm. Okay, summing up an infinitesimal is an integral. So I have the integral of y dm, integral of x dm, integral of r squared dm. Okay, and then pulling out alpha and my acceleration. Again, that comes from this term right here. Okay, so here's what I've got. Integral of y dm, okay, is the definition of my centroid, which is my centroid in the y direction times m. Again, go back to our definition of centroid to prove that to yourself. Same thing with x. The integral x dm is simply the centroid in the x direction times the mass. And you'll remember also that the integral of r squared dm is simply the mass moment of inertia I about point P times alpha. That's where the r squared m comes from. Now, here's what we're going to do, and this is the equation that we're always going to apply. We're going to always sum our moments about point G, because if I sum my moments about G instead of P, okay, or I put P with C, then x bar and y bar go to 0, and all I'm left with is the sum of the moments about the center of gravity equals the mass moment of inertia about the center of gravity times alpha. That is the final equation. Again, the key thing here is you always sum the moments about the center of gravity. Okay, so these are our equations of motion. Sum of the forces equals ma. Sum of the moments about the center of gravity equals I alpha. Now, we're going to apply it to two situations here, and then general motion next time we talk. So, translation. This is where I have no rotation. Alpha goes to 0. So my moments of equations of motion, just the sum of the forces in the x and y direction equals ma in the x and y direction. And the sum of the moments equal g, because again, alpha is 0, so the sum of the moments equals 0. There's no rotation. So that's, if I have pure translation, what I'm dealing with. If I have now the rotation about a fixed axis, so this would be pure rotation. Basically, I've got a pin joint here. This thing is rotating about point O in pure rotation. There's two different ways I can do this. I can sum the forces in two directions. Here I have the normal and tangential. I could have x and y. It doesn't really matter. Sum of the forces in each of those directions equals the mass times the acceleration in each of those directions. Okay, and then I can apply the sum of my moments about the center of gravity equals the moment of inertia about the center of gravity times alpha. Again, that will work. Okay, that's the general equation. However, I can use the moment about point O, and I'll show you why that is. Okay, so the sum of the moments about point O will be I alpha, just like before, but I will also have this r times ma in the tangential direction. I will have to include that. Okay, if I sum the moments about g, that rg goes to 0. Okay, but if I sum the moments about point O, I get that. Okay, rma. It's basically like the cross product of ma. I have to include that if I don't sum the moments about g, which is why we always sum the moments about g, except in this point right here as we move forward. So after I do that, I can separate this out. I got I alpha. And instead of the acceleration in the tangential direction, I'm going to switch that to alpha r, because that is, by definition, the acceleration in the tangential direction. Now what I've got here is I can pull out my alpha, and I have ig plus mr squared alpha. And as everybody remembers from the mass moment of inertia, that is my parallel axis theorem. So this ig plus mr squared actually equals the moment of inertia about point O. So if I have, the only time I can sum the moments about something other than g is if I have rotation about a fixed axis. And then I can sum the moments about that point. Okay, and set that equal to the moment of inertia about that point times alpha. Again, every other time you sum the moments about g, not any other point. The only other time I can do it is if I have pure rotation about some point. I can sum the moments, set them equal to I alpha about that point.